Hello, and welcome to our course. I'm thrilled to have you here and excited to help you begin your journey into the fascinating world of artificial intelligence. In this course, we'll explore three core modules. First, we have Foundations, where we will look at how AI and deep learning came to be and break down the core architectures that power modern AI systems. It's all about understanding the simple building blocks behind seemingly complex technologies. From there, we move on to breakthroughs. Here, we will dive deeper into how scaling up these fundamental ideas creates powerful new capabilities. We'll explore large language models, large multimodal models, and diffusion models, cutting edge tools that are changing the AI landscape right now. Finally, we'll finish things off with applied intelligence. This module is all about real world applications, how to craft effective prompts, build agentic workflows, and consider the impact of AGI on our lives, the job market, and the global economy. We'll discuss not only what AGI could do, but also what it probably won't do, at least for now. The field of AI might seem vast and complex, but at its core, it relies on a small set of foundational principles. Once you grasp these, all the jargon will start to make sense. You will also be able to navigate current and emerging AI tools with confidence. Finally, you will build the skills needed to continue learning independently. You don't need coding skills or advanced math knowledge to follow along. AI is inherently abstract, so this course focuses on helping you build strong intuitions about how AI systems work and how to use them effectively. Start your journey today and unlock the power of AI. It's more accessible than you think. Hello again, and welcome back. In this video, we're going to clear up some of the most commonly confused terms in the field: artificial intelligence, machine learning, and deep learning. They might sound intimidating, but don't worry. Once you understand how they relate to each other, it all becomes much simpler. Let's start with artificial intelligence, or AI for short. AI is just a big umbrella term referring to any technique that enables machines to mimic human intelligence. This could mean anything from simple algorithms to advanced robots to cutting edge language models. Next, inside the AI umbrella, we have machine learning. Machine learning is a subset of AI that focuses on teaching computers to learn from data rather than simply following predefined rules. Instead of telling a program exactly what to do step by step, we let it figure out patterns and make predictions based on examples. Then there's deep learning, which is a special branch of machine learning. It uses complex, layered structures called neural networks that are inspired by the human brain. Deep learning is what's powering many of the breakthroughs you've heard about in recent years, like image recognition, voice assistants, and those impressive large language models. Finally, generative AI is a subset of deep learning focused on creating new content rather than just analyzing or interpreting data. Using advanced models like neural networks, it generates text, images, music, and videos that can closely mimic human creativity. So, to recap, AI is the big picture, any kind of computer intelligence. Machine learning is one way, and a very popular way, to build AI systems. Deep learning is one particular method within machine learning that uses these multi layered neural networks to learn from vast amounts of data. And generative AI, a branch of deep learning, takes this further by creating entirely new content. There's a lot of jargon flying around, but don't let it scare you. The important thing to remember is that all these terms are closely related. Many people use them interchangeably, and so will we throughout this course. By the end, you'll be comfortable using these terms and recognizing the simple principles behind them. In the next lesson, we'll focus on the main goals of machine learning algorithms. Hello everyone. In this video, I want to explore why and how did machine learning come to be, and what makes it different from regular software. Let's start by thinking about the traditional software. In traditional software, you spell out every instruction, every step for the computer to follow. For example, imagine a simple calculator. If the user presses the plus button, you add two numbers. If they press divide, you divide them. Every possible action is laid out in advance. That works great for certain tasks, but it hits a wall once your problem gets complicated. Consider something like an email spam filter. And this is a classic example. You could start by writing rules such as if the email contains buy now, flag it as spam, or if the email includes the phrase limited time offer, also flag it as spam. But you might see the problem already. Spammers change their wording all the time. For example, they might add extra exclamation points. Suddenly, your fixed rules aren't catching those messages. So you update your code to catch these new phrases. But by the time you're done, spammers have invented 10 more ways to slip into inboxes. You're chasing an endless list of rules, and it becomes impossible to manage. Here's where machine learning changes the game. Instead of coding a rigid set of rules, we feed the computer lots of examples of spam and examples of legitimate email. By analyzing patterns in the text, certain words or sentence structures, machine learning can learn which messages are spam and which aren't. The beauty is that it's not matching exact words, like for example, buy now. It's recognizing deeper patterns that make an email suspicious. Maybe spam emails commonly mention a lottery win or have certain suspicious links. Once the machine learning model picks up on those patterns, it can adapt whenever new variants of spam appear because it's relying on what it's learned rather than a fixed list of instructions. This is the core idea behind machine learning. We're letting the computer infer rules from real world examples rather than explicitly writing every rule ourselves. In the next videos, we will look at the building blocks that make this possible, like the data we use to train these systems and the techniques to power them. But for now, just remember, machine learning software learns from patterns, while traditional software is painstakingly coded step by step, often by large teams of engineers. In our last video, we explored how machine learning flips traditional programming on its head, teaching software to learn patterns from data instead of relying on handcrafted rules. Now we're going to talk about the intuitions behind what is a good task for AI to do. The main question one needs to ask is, how would the AI know? And the answer is, from data. Let's think of an example, predicting tomorrow's weather. Weather forecasting is something machine learning can do remarkably well. But think about why that's possible. We've collected decades of data, temperatures, wind speeds, humidity levels, pressure systems, and all of that data contains patterns. By learning from these patterns, a machine learning model can make reasonable predictions about tomorrow's conditions. Without that data, though, the model wouldn't have a clue. It wouldn't even know where to start. Now let's take a very different problem, predicting the winning numbers in a lottery. This is something even the most advanced machine learning algorithms just can't solve. Why? Because lottery outcomes are completely random. There is no historical pattern for the model to latch onto. No amount of data would help because there is nothing to learn. Without patterns, there is simply no way for the model to make an informed guess. Here's another example, teaching a machine learning model to recognize handwritten digits. This is possible because we can collect the data like images of handwritten numbers and label them. The system can learn patterns like the shape of a 1 or the curve of a 5. But what if we don't have enough labeled images to train the system? Then, even if the problem is pattern-based, machine learning can't succeed. It relies on having enough good data to extract patterns in the first place. So here's the intuitive rule. If the problem you're solving relies on finding patterns, and there is enough good data to represent those patterns, machine learning might work. But if the problem is random or you don't have sufficient data, machine learning will fail. This brings us to the heart of today's discussion. Data underlies everything. Think back to our spam filter from the last video. If we didn't provide examples of spam and legitimate emails, how would the model know what to look for? Data is what teaches the system, it's the foundation of machine learning. Let's take another example, this time closer to everyday use. Suppose you're trying to get a machine learning model to summarize a document for you. If you say, summarize this, what do you think the model will do? Without any context, it might give you a generic overview or focus on parts of the document that aren't even relevant to you. But if you specify, summarize this document for a busy executive focusing on key financial data, you're giving the system a much clearer idea of what patterns to look for. That specificity acts as a form of guidance, helping the model extract what's relevant. This is why data and context matter at every level of machine learning, from the massive datasets that train models to the small, targeted prompts you write to get useful outputs. Without the right data, models are like a painter with no paint. They have nothing to work with. So, the success of machine learning doesn't just depend on fancy algorithms or powerful hardware. It depends on data, the patterns it contains, the clarity it provides, and the way it aligns with your task. Welcome back. So far, we've been exploring the idea of building software that doesn't require us to handcode every possible scenario. We saw how machine learning lets computers discover patterns from data instead of relying on lists of rules. Now, let's talk about one of the biggest inspirations behind this approach: biology and our own brains. Decades ago, researchers asked, how do we build a system that learns for itself? Since the human brain is the prime example of a learning system, they looked at neurons, the cells in our brains that transmit signals. At a very basic level, a neuron takes in signals from other neurons, sums them up, and then fires if the total goes above a certain threshold. You can picture it like a tiny decision maker. When enough inputs say yes, it sends a yes signal forward. That's the fundamental idea researchers borrowed. But we didn't replicate the biology in perfect detail, because we couldn't. Computers work in bits and bytes, not in living cells. So we took a functional approach. We asked, what does a neuron do? Rather than, how do we exactly copy it? We just had no better idea for a system that learns without someone programming every single rule. From that humble starting point, an abstract version of a neuron, modern AI was born. We connected these artificial neurons into network, layer upon layer, to handle far more complex tasks: recognizing speech, generating images, translating languages, and much more. But remember, these artificial neural networks aren't exact replicas of human brains. They can be incredibly good at specific tasks, like playing chess at a superhuman level, yet they can also fail in ways we find baffling, like misinterpreting some context that seems obvious to us. While we've borrowed the basic function of a neuron, we haven't replicated everything that makes the brain tick, like the structure of billions of interconnected cells, the chemical signals, or the self organizing processes. As a result, AI can seem superhuman in one domain, yet childlike in another. And that's not just a quirk of today's systems, it's likely to remain true even for future AI agents. They may outsmart us in areas like scientific progress, but could struggle with tasks like require a broad understanding of the world or deep common sense. Machine learning is inspired by biology, but fundamentally shaped by the tools we have: computers. This origin story is key to understanding both the astonishing breakthroughs AI has achieved and the limitation it still faces. We'll continue to explore both sides of that coin in the following videos.